First we will consider the region over which we are evaluating this double integral. So let's look at the limits of this inner integral. This is an integral with respect to r, so the limits are from r equals 0 to r equals 2. So when r is 0 we just have the origin. Points whose r coordinate is 2 are points on a circle of radius 2 centered at the origin. So all these points have r coordinate of 2. Now let's look at the outer integral. So the limits on this must be the limits of angle theta. So theta runs from 0 to pi over 3. When theta is 0, we have points on the positive x-axis. Remember, theta is measured anti-clockwise from the positive x-axis. So all these points here have a value of theta which is 0. We don't include a negative x-axis because the theta value for these points is actually pi radians or 180 degrees. Now theta runs from 0 to pi over 3. Remember, theta is measured anti-clockwise from the positive x-axis, so we measure an angle of pi over 3 radians, which is 60 degrees. So if we take any point in the sector of this circle, its theta value is between 0 and pi over 3, and its r value, i.e. its distance to the origin, is between 0 and 2. So this region here is the region over which we are integrating. Now our element of area in this situation is not a rectangle with sides parallel to the x and y axes. Let delta A be the area of our element. Or theta is the coordinates of this point. So to create this area element we have to increase theta by an amount which I will call d theta. Well, actually I'll call it delta theta, because in the limit it will become d theta. Now the distance of the origin to this point is of course r, because this point is coordinates r theta. Let's get this side of the area element. Well, since theta is in radians, if we multiply r by delta theta, we will have this side here. Again, I should have delta theta here. So that's the length of this arc. Okay, we multiply the radius of the arc by the angle subtended by the arc, which is delta theta. That's only true, of course, when the angles are in radians. Okay, let this side of the increment have length delta r. So that's, we've incremented r by an amount delta r. Okay, the distance from here to here is r, and then we increment by delta r. So now we can get an approximation to delta A. We just multiply the sides together. This is not really a rectangle, but in the limit, as both delta theta and delta r go to 0, then this approximation here becomes exact. In other words, we can say that dA is r times d theta times dr. So now we could write our double integral like this here. So we see that the function that we are actually integrating is not arc times cos of theta, but it's actually cos of theta. We are integrating this function over the region given by this sector. So we see that an element of area is always given by r d theta dr. Okay, now let's go and evaluate this integral. So we want to integrate r cos theta with respect to r, so we treat theta as a constant. So if we do that, integrating r, we get a half r squared. And the limits of integration run from r equals 0 to 2. Okay, plug 2 in for r, we end up getting a half 4 cos theta, or 2 cos theta. Plug 0 in for r, we get 0. Now let's take the outer integral. So as you can see, the result of the inner integral is a function of theta only, and that's what we want, of course. We don't want r to appear in this. If we integrate the cos function, we get sine. We get 2 sine theta. Let's take this example. We want to integrate the function f of x comma y equals x cubed plus xy squared over the quadrant x greater than or equal to 0, y greater than or equal to 0, x squared plus y squared less than or equal to 1. First of all, let's look at the region of integration. Well, we can see that both x and y are positive or equal to 0. So we are dealing with points in this place here. However, we can see that the distance of any point to the origin must be less than or equal to 1. Okay, so this is our point x comma y. From Pythagoras, we know that the distance of a point xy to the origin is the square root of x squared plus y squared. Okay, if we just construct our right angle triangle. So that means that r squared is x squared plus y squared. But we want r squared to be less than or equal to 1. So we have to consider all points inside a quarter circle of radius 1. Points on the circle have the property that x squared plus y squared is equal to 1. Points inside the quarter circle have the property that x squared plus y squared is less than 1. So, if we want our point in polar coordinates, we see that the r coordinate of any point in this region here must be greater than or equal to 0. If it's equal to 0, we have this point here. That's allowed because both x and y can be 0. Okay, x can equal 0 and y can equal 0. And r must be less than or equal to 1. Distance of the point to the origin is less than or equal to 1. Now, what about the range of values for theta? Well, theta can range from 0 for points on the positive x-axis to a maximum of pi over 2 radians or 90 degrees for points on the positive y-axis. Now, for our function, we want x in terms of rn theta and y in terms of rn theta. So that just comes from some basic trigonometry that you've probably seen. So pick a point xy anywhere in the region. Theta, as you can see, is actually an acute angle. So the distance of the point to the origin is r. We know that the side adjacent to theta in this right angle triangle is r cos theta. So that's what x is. And y is just r sine theta. So we have to get x cubed, so we've r cos theta cubed here. We multiply x by y squared, so we've r cos theta times r sine theta squared. And we have our area element dA. So we must multiply the function by dA and integrate over this region. Now, I've just put the r and the r squared together to get r cubed. We can replace sine squared theta with 1 minus cos squared theta, so that should simplify things. Everything will be involving cos theta instead of cos theta and sine theta. So this is just the famous identity sine squared theta plus cos squared theta equals 1. So our integral simplifies down considerably. Now I'm going to multiply r cubed by the r from the area element dA. Now let's consider the limits. Well, we're dealing with a quarter circle of radius 1, so r runs from 0 to 1, and angle theta runs from 0 to pi over 2 radians. So we integrate r to the 4 cos theta with respect to r, so theta is treated as a constant. So we get a fifth r to the 5 cos theta, plug 1 in for r to get a fifth cos theta, plug 0 in to get 0. So the outer integral runs from 0 to pi over 2, and we are integrating 1/5 cos theta with respect to theta. The integral of the cos function is sine. Sine of pi over 2 is 1, so we end up getting 1/5